Welcome to the Community Efficiency Leadership Coalition, our webinar series. Uh, Today, we are going to be talking about integrated building systems, advancing design, air quality, and performance. And those of you who registered know a bit about it, but we're really going to focus on a couple of different learning objectives, and also just kind of examining what is air quality, indoor air quality, really looking at evolution of building design and usage, looking at key historical changes and their ongoing influence, as well as explaining the drivers behind energy conservation and indoor air quality programs. So again, thank you for joining us. I have a few things to go over before we get started. Uh, I want to talk about who we are, that we as SPEAR, as a South Central Partnership for Energy Efficiency as a resource. We are sponsored for this webinar series through the State Energy Conservation Office and the Houston Advanced Research Center. So thank you so much for sponsoring our webinar series. Who is SPEAR? We are a regional energy efficiency organization. We're one of 6 in the nation. Our region is Texas and Oklahoma. We're a member-based nonprofit, a 501c3 organization. We have 65 plus members with a wide cross section of energy efficiency industries, and that includes manufacturers, local governments. It's a pretty wide group, and I very much welcome you to explore our member page, and you can see who we are all connected to. And then also, we focus on outreach education and collaboration on clean energy. My program is the City Community Energy Leadership Coalition, one of several that I manage. I want to highlight upcoming events that SPEAR is hosting, and one is our industry and policy workshop. We are right now, we're very excited. It's going to be in September 18th through the 19th at the AT&T Hotel and Conference Center in Austin, Texas. So I'll put that information in the chat. I highly recommend exploring it. We have some great presenters and a fantastic agenda, as well as for both several of our programs. We have different meetings that are happening at the same time. And one of them includes the CLC program and the Texas Energy Advocates University program, where we'll have a tour of one of the largest power facilities at a university at University of Texas, and we're pretty excited about that. We also have monthly webinars and roundtables, and so I will put in the chat our events page where you can look at our upcoming presentations. We'll be having one coming up that will be focusing on the state legislature. So housekeeping, questions, of course, are welcome in the chat, or you can use the Q&A on the Zoom panel where it has a question mark, and we will answer them either live. I will be moderating during the event, so if you have any questions or anything going on, please put it in the chat and I will get to it as soon as I can. All presentations will be posted on our website. We have an archives page, as well as the recording on our YouTube channel that has over 160 learning. We have a strong learning portfolio. After the event and also during the webinar, I'll be providing a survey that in the chat and also in a follow-up email. If you are looking to get CEUs today, you will need to respond to the survey to receive those CEUs and that CEU certificate. All ICC CEUs will be mailed out within 3 days. So any questions about that, feel free again to put it in the chat and we'll get to it. I do want to cover that there's different ways to connect with us here at SPEAR through eepartnership.org is our website, as well as on X and LinkedIn. And that's my phone number. I didn't put him on the slide, so sorry, Randy, but I do want to introduce, before I introduce our presenter, Randy Plumley, who is our fantastic senior codes program manager. And today he's going to be assisting us with the webinar, and very happy. I don't get to do webinars and collaborate with him very often. So thanks, Randy, for being here.
Yeah, happy to be here. Thank you.
Um, So we'll go ahead and get started. I'm going to introduce our fantastic presenter who, as you may have heard when you jumped on, he has been a pivotal person with supporting Spear throughout the years, including even being right there when Spear got its start as a nonprofit organization. Uh, Today is, again, integrated building systems, advancing design, air quality, performance. It's Jerry Gettler, who has a wealth of information, 40 years of management and professional level experience in design and construction testing, commissioning, and operation of physical facilities. He is a licensed professional engineer in 9 states and certified in many specialties, including commissioning, test and balance, environmental management, and performed commissioning authority and other USGBC lead administrative functions for over 300 lead projects, and is a lead fellow. Excuse me, that is pretty amazing, Mr. Gettler. Without further ado, I'm going to let you take over.
Good morning to everybody. Thank you for joining us today. So what we're going to talk about is a bunch of things tied together. So we're going to go from prehistoric times to the future. So strap in, we're going to talk about a whole bunch of stuff and where it's going. Next. So what we're talking about here is evolution. And this is about occupied spaces, not evolution of people, but it ties together. So we started out in prehistoric times, and this has evolved into complicated systems and buildings that need to be designed, built, managed, and then verified that the stuff is working right. So what we're going to talk about here is to lay a little groundwork and to get your mind set on this is where we came from, and this is a foundation we're building on. A couple of things in the last 10 or 15 years that we've talked about is energy use and now air quality. There's a lot of reasons for that. So we'll go over those and how we got there. So next, what we're going to do today is I'll outline how we got here. What is the evolution? What happened for us to get here? And then what happened in order for us to have such an emphasis on energy conservation and air quality? And there's some good reasons for that. And we're going to also talk about some methodologies for how we got there and who was part of that and what do we see happening in the future. And that's what we're all going to hopefully be part of, is what's going to happen in the future. Next. So let's go back to prehistoric times. We live in a cave. So we had to get some shelter from the weather and from the wild animals and that. But we soon decided that we needed to spread out. We needed to be able to construct our own shelters. So that happened slowly, but that went from prehistoric times, and I just picked 1800 as the base here to stop that section. But these structures in that case had very limited ventilation capability. And they did everything by themselves. Each building was on their own. And about 1800 to 1920, sometime in that period, electricity and lights and fans got invented and start being used, but they were independent for a particular building. So the original, the buildings up until the point where actual real electricity came in had light. It's called a candle. And it had fans. It's called open a window. So the evolution of that, I would imagine, sort of involved around air quality. Is how do we keep the space in this little hut clean? So that's part of the evolutionary process. Then started in the late 1800s, about 1880, when Willis Carrier and his cohorts were inventing air conditioning. And that evolved until about 1950. It's sort of an arbitrary date. So the air conditioning was invented as a part of a building and as part of a process, and was developed. And that took a while because they were inventing things that had never been done before. And then starting at about 1940, which sort of interfaced with the development, the various systems in the air conditioning and ventilation systems developed and used controls and other related testing that goes with that. So the original controls for air conditioning was on off. And then when it started to be controlled by temperature, then we were using air pressures to do that because the electronic controls hadn't been invented yet or wasn't used extensively. So the whole idea there is let's control what is happening in the space. Then in the next 10 years, the complexity happened in a rapid fashion. So we also started tying systems together, and we'll talk a lot more about that as we go along here, and other automation functions. Now, when we get into about 1990, is when the green building programs and the energy programs really started to be put together, and we're going to be covering that in a bit here. So what we're talking about is how did we get here and where are we going with all of these electronic gizmos? Next. So going over what, again, to lay our groundwork so everybody's mind is set on where we were. In the 80s, we're talking about energy crisis. I think it was the Carter administration. And the EPA, an Environmental Protection Agency from the federal government, is working on programs called Energy Star and various other related programs. And there were some ventilation standards created by codes and by folks interested in that. And that was the beginning of the IAQ, or indoor air quality industry. How can we make things better and more livable? That evolved into the 1990s, what was called at that point the green movement, talking about sustainability. How do we control all of the use of all of this energy and make the spaces more usable? And do recycling, because some of the things we're using aren't going to last forever. Some of the programs we're talking about there was Leadership in Energy and Environmental Design, created by the U.S. Green Building Council. And they put their first programs together in the mid-90s. And that evolved into LEED, which their second version of the LEED standard was the one that was actually first published. And there's some other programs related to that. What they call the TRUE program, which is Total Resource Utilization Efficiency, which is a recycling program that the USGBC manages. And then there is an alternate program. Anytime you have one of these national programs, and we'll see more of that here shortly, that somebody else is going to come up with another idea or something to change it a little bit or something to make it more efficient. And that, in this case, was green globes. The 2000s, we ended up with the global warming functions and the concerns, climate change, and the scientists started getting into why is all this happening, and then the contamination controls, and then eventually into carbon reduction. So those are the various programs. The well building was a different organization's version of what a efficient or sustainable building or process should be. It's sort of their answer to LEED. Much more complicated from a documentation standpoint and from a cost standpoint for certification. Net zero programs started working in, and then the other research programs, and there's a program started about that time called the 2030 Challenge, which is an architect out of Santa Fe that put a program together that challenged the designers to design buildings But by 2030, all buildings will be designed and built to net energy use from a standpoint of regeneration and all kinds of other problems or systems. That is also involved into an existing building program that many cities have at this point, that at least or at this juncture are shooting for a 50% reduction, which also ties into the Energy Star and other programs. Next. Again, looking at the various programs again, again, like we talked about, the 90 to 2010, energy conservation, those are the ones we just talked about, Energy Star and all of the rest of that. And in this case, the building codes started picking up on this. So what we find is if we watch the context and the contents of building codes, and we'll go over some of those here in a minute, that they pick up on these things that the society and the government and the organizations want, and they put together basically minimum standards. That's what basically building codes are, is buildings net processes and minimum requirements. Again, the 2010s, performance, net zero, carbon reduction, all of those things we were talking about then. Things like the Living Building Challenge program and the Passive House, which are net zero housing, and various other industry and government programs. In the 20s, the ASHRAE folks got even more involved, talking about building occupant health. The pandemic, the COVID-29 program, and the occupant programs accelerated that tremendously. So we're seeing more literature and more development recently in the last few years in air quality and that sort of operation, as opposed to straight energy savings. Again, well building, fit well is a reduced requirement process similar to the well building. And then we're also talking about all of this electronic stuff, all of these things that control the various building systems, and we'll talk about those here in a minute, that get tied together, including all of the computers and all of the communications that, we're not all sitting in a theater looking at a movie here. We're looking at a presentation that's being done over the internet. So all of that is tied together, and that causes not only opportunity, it also causes some problems. Next. So again, real quick, 1970s were conserving energy. In the 90s, we're starting to look at what kind of health threats we're going to have, greenhouse gases in the 2000s, and how we're going to reduce that, improve human health in the 2010s, health and well-being, the 2019, 2021 is fight disease. And that's going to keep going. That's not going to stop. We're not going to sit in one place for a while and be able to catch up. So it's all happening at the same time. And we're all going to have to hang on and see what we can do to improve our situation and everybody else's. Next. So let's talk about the codes we talked about here for a minute ago. First, we got the building codes. And that building code is an evolution of what the requirements are, because you can build a building, you can go back to the old hut process, but that's not something that the cities or states or countries are going to put up with or allow. They want it built to a certain minimum standard. Same thing happens with the mechanical, plumbing, and electrical. They all relate. And they're minimum requirements. And this is one of the things to consider when we're going through the process here is building code is one thing, that the other ones are subservient to those. And the same thing happens to these other codes. Energy code started, like I said, in the late 80s and the 90s. And the IECC, International Energy Conservation Code, the 2024 version is what relates currently. That's the latest one. Every 3 years, these codes are republished. And it relates, in this case, the energy code relates to ASHRAE standard 90.1 based on 2022. And a lot of the information and numbers and permit areas in the energy code relate to the 90.1. The same thing happens with the green codes. And that, again, started in the late 80s and 90s. The green codes, the International Green Energy, IGCC is the Energy Conservation Code. And the 2024, again, is the latest one. And it relates to the 189 standard for design of high performance green buildings. The interesting thing is that the green code is constructed a little bit differently than the energy code, in that the energy code has a separate committee. And of course, the ICC has separate committees for all of these. But the energy code is pretty much independently written and developed by the ICC with input, as I said, from the 90.1. One or two issues ago, the ICC decided that on the green construction code, that the first chapter, or the admin chapter, was the thing that they were going to develop. And in the meantime, they were going to adopt virtually all of the detail and the verbiage in ASHRAE 90.189, excuse me. That is, if you look at a copy of the 189 and lay it next to the IGCC, they're virtually identical. And in the meantime, we talked a little bit about all of these green and certification programs becoming popular with people that want to build and have their building certified. One that produces a better building, and it also allows them to lease or sell the building better, or it may be a decision that both the owner of the building makes, or in some cases, we've worked on projects where the insurance company insisted on a green building certification. And there's a whole bunch of reasons for these. But again, these are things that are in process. They're moving. They don't wait for every 3 years. The lead now is on a version 5. It was just released. So all of this emerges and then keeps growing. Next. So what are we really looking at here? How to optimize all of this. So what is the building process? What do we have to do if you look at the basics? You have to set some requirements. What is a building supposed to do? What is it supposed to meet? What is it supposed to produce? Who's going to live in it or work in it? That all needs to be documented so that people going from there forward know what they're supposed to be doing. And then the design, detailed design from an architecture standpoint, meets those requirements. Who's going to check on that? And then from there, it goes through the normal plan review process and the municipal processes. Then if it meets the requirements for the local municipality, then it gets built. So the construction has to follow those documents. Somebody has to be sure that does meet those requirements as far as the building goes, and then the various systems we talked about, and we're going to discuss a lot more here in a minute. Who's going to test those? And they have to be verified. And a lot of these systems don't talk to one another like they should, or aren't programmed together. We'll talk about that. And then, since it's more complicated now, the operators need to be trained. Who's going to run the building? Do they know what it's supposed to do? And where's the documentation? How are we keeping track of all of this? Next. So if you look at things in I've broken these down into 2 categories. What I call base building, which is not the building systems. To build a building, you got to put it on something. Normally, you got a site. You have a foundation that goes through the structures. You build the enclosure, build the box everybody's going to work or live in. Put windows in it if you want to see outside, or from outside to inside. The roofing gets installed. All of that gets insulation. just about every one of those, the enclosures, the windows, the roofing, the insulation, all impacts energy use. So the whole idea there is these are things that we have to be careful about if we're talking about energy use and air quality. So going over to the other side, the right side here, systems, and I sort of put those in a list of how it got developed and how it ended up in buildings. Electrical systems, you need those in order to run most of everything else. So those systems all have to be communicated with, the electrical power and emergency power and all the rest of that. Air conditioning and heating, we're talking about ventilation, but we're also talking about heating and cooling. We're talking about being sure the building is pressurized to keep the controlled atmospheres in the building and the hot air or very cold or wet air outside. So all of that takes controls and monitoring. Plumbing, you say, well, that doesn't connect. Well, it does, because you've got hot water systems, you got water meters, and you've got a lot of other things that do, in fact, at times connect to the building process. Fire protection, fire sprinklers, again, sort of independent, but the alarm systems connect to the master systems. Security systems, building access, happened within the last 10 or 20 years, but those also certainly have to communicate. Safety and fire alarms, again, the same thing. They have to communicate. Telephone, obviously, that has to be part of the communications process. But we're finding the telephone, in many cases in office buildings or commercial buildings, telephone systems are connected to the computer communication systems. So we've got these various other communication systems. And we also have to talk about computer and connectivity. So the whole idea here is all of this ties together. So who's watching that and who's being sure that it gets coordinated? Next. So who's managing the design, construction, and operating a building? The design is performed by a group of architects and engineers and that, quite good folks, usually coordinated by somebody, usually the architectural firm, but it has been other folks. But those folks talk to, they communicate to a certain point, but not perfectly. Field construction, coordinated or managed by somebody, usually a general contractor or construction manager. There is the fact that that particular person or group does not know all of the details of everything. So the actual construction of all of these elements and systems are usually performed by independent subcontractors. There's usually limited communication. What we find is a lot of these subcontractors don't talk to one another out in the field. So they say, well, my system works, but they don't know whether the system next to them that's supposed to be connected to them works. So that's got to be watched and verified. They're interconnected to computerized control system. And it gets to be interesting because these control systems are often cloud-based. And that gets some interesting problems and also opportunities. In the past, the computer that ran the building was in the building. Then it starts spreading out. Then it got with all this AI capabilities and ended up in clouds. And that's, which is good to a certain point, but it also exposes the building to certain dangers. I remember asking at a trade show a few years back, some of the folks at ASHRAE that were developing these interconnection computer programs. We talked about that for a bit, and I says, if you got a building that's being controlled in the cloud, what's going to keep Valdemir from taking over your building? And they looked at me and said, not much. Next. So The IECC it's again, we're talking about here verification of what's happening here. So continuous air barrier, usually it's part of the code requirements, so the code officials are interested in that. And the code here says, and this is the code paragraphs with the 2024 energy code are on the top of the slide here. But the code says a registered design professional or approved agency review the documents, inspect the air barrier, and then produce a report provided to the owner that says all of this stuff was found, was fixed, and it works properly. Next. Okay, maintenance and information. That's the next C408 paragraph. Those paragraph numbers are up on the top of the code information. So the maintenance information, 40811, building operations, it's a requirement to provide to the owner in various documents. He needs to have a record of the specifications and designs. How did it get there? What was it built to? It also needs more information about what the manufacturers actually produced and that was installed, which is the submittals. And then the programs, how is it set up? What is it supposed to do? What are the data points? And then all of the installation, maintenance, and operating procedures, and what the construction or verification industry is calling that is a systems manual. And we can go into that a little bit more later, but it's mainly part of a commissioning program or seminar if we could do that. So the equipment labeling and all of that has to be done. And so that the maintenance folks know how to track what the thing was built to documentation, so they know how it's supposed to be maintained and how it's supposed to be operated. Next. 408.2, talking about solar and mechanical systems, or excuse me, hot water. Documents include system operation requirements, commissioning and completion requirements, plan drafted by the commissioning provider, prior to final inspection. All of that stuff has to be documented and presented to the owner so that he has it so he can operate the building. And in some cases, the AHJ may want to see it if requested, but in most cases, that's not provided to the AHJ because it gets pretty complicated. Most all of the cases now, all of this is in electronic format, so it's computerized. I remember one of the first buildings that we did, I think it was in 2004, we did a systems manual in 3-ring binders. This was 2 4-story office buildings, so the systems manual included or totaled up to 27 3-inch 3-ring binders. It's a lot easier to do that on a computer. Next. Maintenance information. And here we're talking again about commissioning or verification plan, 40821, provided by the design professional or approved agency. They want a narrative description. How is this stuff supposed to work? What are the verification or commissioning activities? What are they supposed to do? And then it's not only just one person in this case, certainly, but it includes a list of equipment, what's supposed to be tested, and what is it supposed to do? What criteria does it meet? They include calibrations and economizer, all kinds of other things that are in the 408.2 and in testing conditions. And then that has to be reported. In other words, what is it doing? Is everything that's listed supposed to be working? Is it working properly? And it includes measurable criteria. What is the building or a particular system or a particular pump or chiller? What is it supposed to be doing? And then measure it for that. Next. So it also talks about 408.2 talks about testing and balancing to accepted industry standards, so that testing and balancing is a requirement. Air system balance, we'll talk about details there for outlets and terminals and that. And it references to the mechanical code. The mechanical code refers to testing, but it doesn't ever refer specifically to this particular process. Hydronic system, same way. Individual heating and cooling, all of that needs to be balanced. That's a requirement of the code. And then test and balance report required and is reviewed by the verification team and is included in the systems manual. And if the building official, and we have a few building officials occasionally that ask for that to see what the building is supposed to be doing, particularly if you're looking at, for example, municipal buildings. So certainly the building official is interested, or medical or research buildings. Sometimes they want documentation on that. Next. Maintenance information. Testing is required, demonstrate installation and operation. In other words, is it working like it's supposed to? Is it working to the specifications in all modes and sequences? So you have to test all of that. And then all of that needs to be documented based on the plans. And then in this case, somebody in the code writing organization apparently liked economizers. So all of the codes have paragraphs about economizers. So that is all included in the testing and in the reports. Next. So you have a preliminary report because depending upon weather in this area of the country, certainly, we have hot summers and cold winters. So if you have to test a boiler, then if you're trying to do that in the middle of July, that gets to be a problem. And if you're testing a chiller in January, that's a problem, or a cooling tower. So you have a preliminary report. So once the building is essentially complete, then you test all of that and you make up a list of what wasn't tested or what needs to be adjusted or changed in order to make everything work. So all of that has to be itemized so that the contractor and everybody knows what they need to do, and the owner knows what still needs to be done. So all of that gets into the functional performance testing. Next. So once that next version is produced, in other words, once you get to the end of construction, and here in the code in 482, it talks about the final report needs to be provided to the owner within 90 days of the project certificate of occupancy. That can be a problem. So what the industry is basically saying is that needs to be provided to the owner at the end of before the end of warranty, which is usually a year. So usually it takes probably 6 to 8 months to get to the maximum demands so that you can test these things. But you need the final test and balance report, final test procedures, what was fixed, results of the performance test. So here you've got a complete report of everything that needs to be tested that's actually working, and here's the results. And here's what the efficiencies we found, and here's what corrective measures were taken, so that the owner has all of this background information. Next. Lighting systems, some of the lighting in 483 that basically the lighting systems and the lighting controls were written by a different subcommittee apparently, so that the functional testing, the lighting and controls are part of the final inspection. Again, certified by the registered design professional or approved agency. And here what the lighting is looking for is occupancy sensors, time switches, daylight response, O&M manuals and reports. All of that has to be included specifically for lighting systems. Next. Existing buildings, what happens if you're remodeling or adding to something? Well, the code says if you're adding to a building, the additions need to conform to the new construction requirements. So a building built back in the 80s and you're adding to it in 2025, that building addition needs to meet the current requirements in the codes. Alterations, same way. If you're changing something in the building, like new air conditioning, hot water lighting systems, changing lighting from fluorescents to LEDs or however you're doing that, all of that, if you're changing it, it's got to comply to the new requirements. Repairs, replacement, straight replacements, not normally required. And then if it's a change in occupancy, if the energy use changes, then it's got to be modified and updated to the new requirements. Next. So here's a list of things that impact the usage and cost of energy for a building. Again, it's things that we've already talked about, but these are all of the things we have to consider in designing and in building and in testing. What's the owner want? Where is it? Who's going to occupy it? What kind of schedule is it going to be on? Types of mechanical equipment and controls, either by code or by owner requirements or by process requirements. Type of lighting, what are we talking about? Putting in the building or in the process. Control systems, usually computerized, but not always. Any equipment that uses power, electrical systems, and how do you get power to the building? You use a net zero with solar cells, or do you use a different system? How effective is the installation and verification process? How are you going to? So somebody needs to say you got to do this. So what kind of maintenance and processes and effectiveness? So if the green building system is used, you get a better performing building, but it also might cost a little more. But LEED and well building, fit well, and the others give you a lot of guidelines for saving energy and making the building better to operate and better for the people in the building. Next. So the cost factors for a building, it's pretty obvious. What's the code require? Texas codes as a baseline are still based on the 2015. Most cities have now changed, at least in the North Texas area, have changed to the 2021. Some of them even looking at the 2024. And the state is considering through SECO the opportunity to change the 15. In fact, that's part of the law is for them to have to look at that and then update that requirement. And that hasn't been done yet. So cost factors, types of buildings, what are you doing in it? What's the mechanical system? What's all of the things that go into the building and in the operation? Energy supplies, what's available? And the computerization systems, the AI computer banks are about to use a whole bunch of energy. Is it available? We have the same problem with putting items in areas that don't have the water that they need. Now, all of that's cost-based also. Record keeping, local weather conditions, all of that affects energy cost for a building. So the requirements of energy using processes, what's in the building? Is it a bunch of computers? Is it a manufacturing process? All of that affects cost of operating the building. Then what do the occupants want? What do they need? Is it a research building that the occupants is important? Computerization? All of that is important. Next. What kind of opportunities do we have? How do we look at this and say, what do we do with it now? How do we change things? How do we update things? Equipment types of rooftop air conditioning or built-up air conditioning units, the setup and the scheduling of these all get involved in energy cost reductions. Supply availability can rate into time of day rates. Sometimes areas will have demand control options so that at a certain demand level, the building is notified by the utility to cut back on the agreed to systems. And they cut back on that, and that saves them utility cost as well as usage. And then where are you getting your energy? It's an electric utility. Are you doing it with windmills and solar panels? Not natural gas. That's an energy source. But that also has energy conservation as part of it. What about the building interior conditions? about process controls and variations. All of that gets involved in the energy use. So occupancy conditions or requirements and needs, guess what? That generates a need for air quality. What are we talking about there? Next, air. What is it? Why is it important? Well, we got to have air to breathe. We got to have air to survive. Necessity for human survival. It consists mostly of oxygen and nitrogen, but small portions of other materials can be in the air that cause problems. And we'll talk about some of those here in a minute. Cause the problems for the humans in the space and the materials in the building. So basically, the human body requires a continuous supply of air, obviously. That air supply needs to meet requirements, usually because the Environmental Protection Agency and some of other organizations have standards, including ASHRAE. They said it should not contain harmful levels of contaminants, but they can cause illnesses and even death. So these contaminants could, in various gases and volatile organic compounds, particles, and we'll talk about here in a minute. But there's a lot of things that float around in the air that we don't normally either see or consider until there's a problem. Next. One of the things to consider is, why are we doing this? American adults spend about 90% of their time in buildings, unless, of course, you're working an outside job. It's important to comfort and health, but it also indicates clean air improves the productivity. And we'll show you a research study that has verified that. The building systems include the capability of providing clean air along with monitoring that air quality. It's important, and it's getting an awful lot more attention in the commercial press, in the building industry press. You'll see a lot of information about air quality and what is happening on that. So we're talking a lot more about energy monitoring, sensing, who's watching what, and the building should have capability to provide that filtration. Sometimes you might want to change and upgrade that filtration, but there are limits there. And these systems should be designed into the buildings, but what happens to an existing building? That causes some interesting challenges. So, but anything that you put in needs to get verified. It needs to get tested. So you got a record of what it's supposed to be doing. So you can go back later and check and see if it's still doing that. Next. So what do we decide is what is good air quality? ASHRAE and just recently, in February 12th of this year, 2025, reviews multiple studies about the CO2 carbon dioxide levels. And for many years, it was said that 1,000 parts per million in the air can be CO2 as a limit. But that's discussed based on the research. They've decided that the 1,000 is not an absolute limit for all spaces. So that throws a wrench in setting a standard, and that's got to be it. But they can be used for monitoring and building ventilation control systems, and most of these systems do. The US EPA, National Association of Quality Systems for the United States, describes air quality contaminants and potential limits. So those include carbon monoxide, lead, nitrogen dioxide, ozone, particulate matter, and sulfur dioxide. And there's a bunch of other things to watch, but this is what this particular study covered. Next. ASHRAE 62 is often cited as the ventilation standard that most folks use and follow, and it's cited in standards and codes and all the rest of that. Ventilation indoor air quality defines acceptable air quality with interior building equipment and their performance levels. It's sort of obvious there. The impact on the building includes, of course, outdoor air quality. It's something that's important to, if you're ventilating the building, what kind of air are you sucking into the building? What kind of systems and equipment? And there's a chapter on that in 62. And then procedures for evaluating these and for designing these, construction and startup instructions and operations and maintenance. All of that information is listed in ASHRAE 62.1. And there's 62.2, which is various other parts, other types of buildings. And that goes on for 2 or 3 other 62 standards. Next. So what kind of contents are we talking about that determine air quality? Obviously, comfort, thermal comfort. We're talking about higher temperatures and levels of water vapor or humidity. So that has a feeling of discomfort. That's the main system. Carbon dioxide, we talked about that a little bit here. Human breathing in and out. But if you get too much carbon dioxide, because the human body needs the oxygen, it'll put up with some of the other stuff. Impaired cognitive abilities, drowsiness, nausea, and a few other things. We don't often consider that that's carbon dioxide, but it certainly might be. Particle matter. Talking about things from construction, from carpeting, from wildfires, from cooking. But in this case, particle matter, and there's measurement criteria for sizes of the particles, and we'll talk about that in a minute, that ear, nose, and throat irritations, coughing, sneezing, all of that, shortness of breath, all of that is affected by the particulates. But the interesting thing is if you look at the human risks, a lot of those cross over. So when you have a problem in a building, you need to figure out what the real reason is and test for that. And you can't just test, ask somebody, test my building for air quality. Well, the issue there is if you look at all of the things on the health risks, the various things that could happen, and if you look at all of the chemicals on that, which we'll look at here in a minute, that could be, so what you can test for in the range of thousands, and I think there's something like 100,000 different chemicals and materials in the government listing of materials. You can't possibly test for all of that or afford to test for all of that. So it's usually best if you're having a problem in a building is to categorize the symptoms. And then whoever is doing the air quality, once you tell them that, should say, okay, we need to test for this particular parameter. So it's we can't just somebody on the 36th floor of an office building saying, come test my air quality. The answer question to that is for what? So you have to be more specific in that, and we have to be able to have our controls and our supplies of air respond to these things automatically if possible. Volatile organics, it's one of the biggest problems that we have because it's in building materials, furnishings, cleaning agents, even the occupants. So that there are things that the occupants bring in. So if you get a very well built and ventilated building, your biggest contaminant causer are the people that come into the building for multiple reasons. But anyway, on the health risks on VOCs, you get eye, nose, and throat, headaches, nausea, all kinds of things that can make people unhappy, not liking the space, complaining about it, or sick, which we'll talk about here in a second. Next. So what can cause these problems? So you're talking about building components and the paints, caulkings. You need to be careful about how you build things because they have VOCs and particulates, some of which the VOCs will air themselves out. But again, you have to understand each one of the materials and each one of the pollutants. Mechanical systems can cause you problems, and chemicals. Furnishings, certainly. Carpet, textiles, deteriorated furniture is something. We have found up until recently that some of the furnishings in office buildings, if you have a partition system for the cubicles, If they're made, sometimes in the Far East, they have high levels of formaldehyde, which will air out after a while. But if you understand where these things are coming from and what the normal contaminant and response is, you can identify that a lot easier. Office equipment, again, copiers are one of the biggest problems with both ozones and VOCs. Supplies, solvents, toner, all kinds of things that can outgas. Cleaning, and we're figuring when you do heating and or cleaning and housekeeping, everything's going to be great. Well, you're also spraying things around to clean things. Air fresheners, which are actually chemicals. They smell good, but they put chemicals in the air. And of course, airborne dusts. Maintenance, all of the things we do for that can spread VOCs around. Pest control, pesticides, who knows what's in those? So occupants, deodorants, cosmetics, all the rest of that stuff, they contribute to the contamination in the space. And of course, food and snacks and their problems. Next. So what are air quality solutions? How do we fix this? Well, you got to design it properly, understanding that there's more than just code requirements here. The issue there is there's minimums and then there's requirements for what the owner wants and what the occupants and processes need. Selecting materials that don't outgas and don't contain the materials, maintenance and cleaning, airing buildings out, control and monitor systems are getting more popular. They're not cheap, but they do assist greatly in the operation of the building. Verification and testing. What happens there? Who's going to test all of this? Because all of the systems we were talking about before, every one of those systems is built by somebody else. Who's going to verify that they connect together and work right? So adjustment, building systems, increased outside air ventilation, filtration, all the rest of that, and all of it causes problems. And change of the various problem materials. So the outside ventilation, we did a inspection on a private school, a year or so ago, that had about 7 or 8 buildings that each had rooftop units. There were 2 and 3-story buildings. Each one of them had rooftop units. So we looked at all of the rooftop units, and of the about a dozen rooftop units, only 2 of them had the outside air even open. And walking into these buildings, you could tell. So saving energy often is counterproductive to air quality. So we have to consider that as we operate buildings. Next. Here's the things that we look at. What do we test for if we're going to test a building? So contaminant testing, various contaminants. There's 2 different levels of the testing, and the lead version 4.1 has listings of that. The list here on this page are basically sensor handheld equipment that we can test all of this with. Somebody walking around with a couple of instruments, and we can test all of it. Temperature and humidity, of course, straightforward, not really contaminants, but important to understand the rest of the systems and the rest of the responses. Carbon dioxide, we've talked about the importance there. Target in that case is for lead is minus 900 parts per million. Carbon monoxide, where do you get that? Well, if anything, it got combustion information, what's happening. Carbon monoxide and ozone and nitrogen dioxide, if you have diesels in the parking garage, that all gets to be an issue. And then particulates. Remember that the PM10, which is a large particle mass 10, that basically your nose stops most of that, and nose filters. But the 2.5 particles, which are very small, get all the way down into your lungs, and that can cause serious problems. Next. Now we get into the VOCs, gets to be more complex, and these samples and the analysis of these involve certified laboratories. And there's not too many of them in the country that LEED and a few other organizations will accept. But here we're talking again about the formaldehyde that is serious problem for a lot of folks. And then the related acetaldehyde, they're called aldehyde standards. Benzene, which is a common solvent, hexane, and all the rest of that, all the way down there. Trichloroethylene or tetrachloroethylene, xylenes, all of that are various different volatile organics that can cause some serious problems. So what do you do when you get all of this put together? Next. So if there's been some interesting university studies. Why do you want to do this other than people aren't complaining? Well, it's more than just health. It's about cognitive function caused by air quality and standards that affect that air quality, and productivity of the folks in the building. So health and productivity is really important, and the Harvard folks have done some interesting studies on this. Next. And if you want to get more information on this information is available to you. Go to the Harvard University website and ask it for the COGFX study. And there's at least three different reports from 3 different study systems that they've done, all called the study reports. One of them's local, one of them's national, and the other one's international. So the 3 ventilation strategies and 4 different heating and ventilating systems, and we'll explain those here in a minute, across 7 cities, found that the indoor environmental previously associated with a doubling of cognitive function test scores can be achieved at an energy cost between $14 to $40 per person per year. Golly gee, why do I want to spend all of that money for each person in the space? Well, the result of that study says for spending that much, you get about $6,500 equivalent of improved productivity per person per year. So the productivity of the people in the space are very important. But the energy efficient technologies found that the energy cost to between $1 and $18 per person per year, that's the same thing as the equivalent of about 0.03 cars on the road per building per year. Not much. So we're talking about saving a lot with clean air. Next. Here's how they did it. Sorry about the quality of the slide here, but the top shows a cubicle system that they set up for a group of folks that worked there for about 2 weeks that they tested under various conditions. The bottom slide or bottom part of the slide shows the mechanical systems that allowed them to do this particular study. Next. So they got 24 professional level employees, 6 days over 2 weeks. So what they did is they says, what's the typical atmosphere? Well, that means high CO2 levels and high VOC levels. So it was, normal, uncontrolled office space. So then they controlled the office with two tests where they lowered the CO2 levels with ventilation, left the VOC level the same. Then they had controls they could do this. And then they tried it the other way, lowered the VOCs, but left the CO2 high. And then in the end, they lowered both of them and then tested and then compared the response performance of the folks to the first and last tests. What they tested was activity level, applied activity, focused activities, task orientation, crisis response, information seeking, information usage, and breadth of approach strategy. Results that green building, which you changed one contaminant, the performance level was 61% higher. the average performance level on a green building, or both criteria being controlled, was 101% average higher. So you had better cognitive functions, fewer health systems, better perceived environmental air quality. In other words, less complaints. Next. So again, this list, and sorry about the fuzziness here of the slide, but if you notice that of the 8 they were looking at, 2 of those items, the strategy and the other one, averaged about 300%, 3 times better the response of people in the space if you control the contaminants. Next. So the problem here is you've got all of these systems designed, installed, operated. And these are the same lists we talked about before. Who sets the requirements? What happens, the design? Is it designed that way? Is it built that way? Hey, how about testing it and verifying it? Who's the who trains the operators? Documentation and records. Found an interesting story recently about whose job is it anyway? So the little paragraph here, this guy is attributed to a guy by the name of Charles Swindell. Story about 4 people. They're named everybody, somebody, anybody, and nobody. There was an important job to do, and everybody was asked to do it. Everybody was sure somebody would do it. Anybody could have done it, but nobody did it. Somebody got angry because it was everybody's job. Everybody thought anybody would do it, but nobody realized that everybody wouldn't do it. It ended up that everybody blamed somebody when nobody did what anybody could have done. Interesting way of looking at this. So one of the things that the industry has come up with is a performance system, or a testing and verification system, and the codes recognize this. Next, what's called a commissioning provider. The idea here is that you have somebody at the beginning that lives through the entire process. The only entity in a modern construction process that uses commissioning, the only person involved or group involved in building a new building, is the owner and the commissioning provider. So they are involved in the entire process. So this definition from ASHRAE Standard 202, which is a commissioning standard, the process focuses on verifying and documenting that all of the commission systems and assemblies are planned, designed, installed, tested, and operated and maintained to meet the owner's project requirements. Oh, wow, that's a bunch. But here you have a process. Commissioning is a process, it's not an event. So we've got a lot of things to look at nowadays. We've got, of course, the environmental issues, the energy issues. All of this now is tied together somehow. And we've got to be concerned about how are we meeting all of these? How are we going to make the buildings that we're building safe and healthy? So there's a lot of work to do here yet. So next. So any questions and comments? Randy wanted to be sure that I got my picture on the slides here. So that's on the slide here. If
That's
anybody
about
has,
right.
yeah, anybody has,
Jerry, I did look for your picture in
yeah,
places.
yeah.
And I couldn't find one. So I think
So,
I'm going to save this one.
yeah. So my email is there if anybody wants to ask questions later or whatever. And we talked about the availability of these slides because there's a lot of information that might be useful to folks.
Yeah, we do have one question, and it's who offers training and certification for this air quality issue?
ASHRAE. ASHRAE has programs for that. Environmental Protection Agency has training programs on that. There may be other ones also, or organizations that are involved in the air quality process. There's more people offering the organized training from a commissioning and testing and building standpoint than air quality, since air quality is a fairly new function. But the EPA, as long as they're still existing, and having those programs, that has a whole bunch of different things that they could offer on that. And there's some other ones too. The NIBS people, the National Institute of Building Science, up in Washington, can direct you to some the air quality as well as the building construction processes. So that's the whole idea there is it's a moving target. Since the other thing is on the air quality, forgot to mention it, talked about the effect of people in an office building. What they're finding, and Harvard's doing some interesting research on this all now too, is that certain contaminants will affect children more than adults. And the interesting thing is what they've traced is that the results of some of these contaminants will affect the children in the womb that haven't been born yet. If the mother breathes that particular contaminant, it may affect the embryo. So there's some interesting things. It's an ongoing process, but those are the things that that we're looking at right now, and they keep it cascades. So those are the folks that I'd start with, and there's probably other ones that that if you run into a roadblock of not finding anything, shoot me an email, and I'll look up some other stuff for you.
Thank you so much. Really appreciate that, Jerry. And then I am putting some of those resources that you had mentioned in the chat. So I put ASHRAE's Learning Institute as well as the EPA and their training program and videos. Let's see if there's any more questions. There was one question regarding where are you from, Jerry? Where are you
Where am
located?
I from originally? Yeah.
Where are you located right now?
I'm located right now down in the city of Dallas, in the Republic of Texas.
All right, all right. Well,
And
thank you.
I came from Missouri. Went to school up in Missouri University or Missouri Science and Technology, and I've been doing this air quality stuff for about 30 years because it's an interest of mine.
Well, you are a wealth of knowledge, and I learned a lot today, and I am sure several people that are attending the webinar have as well. And I want to go ahead and bring us to a close for our webinar, but there'll be more coming up. Please just look at our events calendar. And thanks again, Jerry, for sharing your time and expertise. I learned a lot today. And thank you, Randy, for sharing your time as well. And we appreciate all those of you who participated. And as I put in the chat, the CEUs, we'll look at seeing if we can extend them for the extra time that we got to an hour and 15 minutes. And all right, well, we'll see you all next time.
Thanks, Jerry.
Thank you,
Thanks,
everyone.
everyone.